All right, so the plan going forward is today I have formally finished the decision tree and ensemble methods. Now, I don't have time to talk about some very useful models like support vector machines and neural networks. I don't have any time to talk about them, but I have my slides. Okay, so if you're interested, you can always read the slides and take a look at the. I haven't uploaded the R codes yet. I will do that. So you can take a look at the slides and take a look at the coding. If you're interested in these topics, you can use my slides or read a book to study on these topics. Because we have very limited time in this course, I'm going to start talking about causal inference finally. So this is our first lecture. Just like when we are doing the statistical learning, I'm going to spend the first lecture in terms of foundation. So we're going to say foundation of causal inference. Okay. So after our foundation course, we'll discuss more about detailed causal inference way of doing causal inference. Okay. So let's start. As you can see, we have 241 page slides. So this is a large lecture. I'm going to spend quite some time on this foundation. Maybe it will cost us at least two weeks, or maybe 3 weeks. So we are left with about 2 weeks to do the rest. Okay. All right. So some of the stuff about causal inference I've already talked about in my introduction. So I hope everybody's already familiar with that. Causal inference is concerned with two things. Whenever we study statistical models, random forests, Bayesian models, or lasso, right? So whenever we are studying those kind of models, our goal is to try to obtain the best prediction or the best sort of a modeling of the underlying statistical relationship. We're not interested yet in causal effect, right? But causal inference is interested not only in how to use X to predict Y, but we want to know whether X has actually any causal effect on Y. X and Y can be correlated without any causal effect. So in causal inference, we want to separate them. Right? We want to separate the pure statistical correlation from a meaningful causal effect, if you will. So causal inference is concerned with two kind of things. The first thing is what I call the causal effect learning, which is simply learning the causal effect of X on Y. So I just want to know if X is the causal effect of Y, if so, how much. That's causal effect learning. Causal mechanism learning is more ambitious. Not only do I want to know if there's any causal effect, not if there exists, I want to know what the mechanism is. Right? So if we discover that X has a certain amount of causal effect on Y, then the natural next step question is, what is the mechanism that give us that kind of effect, right? So that's called causal mechanism learning. It turns out that the majority of research in economics, applied economics, is causal effect learning. So we simply give you an X. I want to know the effect of policy, a certain government policy, or I want to know the effect of certain company firm action on some kind of Y, right? And that is a causal effect. So we're trying to learn that effect, but we are not so good at actually learning the underlying mechanism. So oftentimes, what the way that people are doing things right now is that theorists, people who specialize in drawing up theory, they try to design, like this, to try to come up with theory about the underlying mechanism, and then of course you can test those mechanisms by taking them to data. But we don't really have a way of automatically discovering mechanism from the data or learning from data. Right? So causal mechanism learning is harder than causal effect learning. Okay, so I don't need to talk about this. You don't know? Okay. I'm not sure, did I talk about this in introduction? Okay, so this is a story by Bertrand Russell on why learning causal effects is important. Okay, so you can, if a chicken, there's a chicken that is pretty smart, but not smart enough. So the chicken sees somebody come to feed every morning. Whenever the sun rises, somebody comes to feed him. And so the chicken, based on this statistical pattern, which is sunrise, people come, the chicken infers that there's underlying relationship. Whenever the sun rises, people will come to feed him. Until one day, of course, somebody comes and and cut him, right? And kills him. So for the chicken, right, the statistical relationship is correct, morning count, but unfortunately, the problem for him is that he doesn't understand the underlying causal relationship, right? The underlying causal mechanism. He doesn't understand why people come to feed. He just sees this correlation, and because of that, he didn't run away first, and then he died. Okay, so this is the sort of story about why it's important not only to see the correlation, but also to understand the underlying mechanism. Right? A slightly more realistic example of people suffering from the understanding mechanism would be something like the financial crisis, where before 2005, when the housing price started to go down in the U.S., the Wall Street, on Wall Street, those banks issue a lot of collateralized mortgage debt. Okay, so the CMOs and CDOs mortgage debt, and then when you issue those collateralized debt, you need to include a lot of housing debt into your pool, and then you need to make them into tranches. But the statistical task for people who are trying to pricing those things is try to estimate the probability of people default. Right? So each housing loan, what is the probability of default? What is the probability of you default? What is the probability of that default? And how do they get this default probability? They estimate the probability from historical data, right? Which is correlation. And in historic data, unfortunately, the data goes back only about 10 to 20 years. But the U.S. housing price has always been increasing for a long time. Before 2005, the U.S. housing price has been increasing for like 20 years, non-stop. So in other words, and then in those periods, you do see very small default probability for a lot of people. Why people have low probability of default? Well, because housing price is always increasing. You purchase a house, your housing value is always increasing. So even if you run out of money, you can always refinance using the higher housing value. Okay. So in other words, do we know? Can we, based on this historical data, can we ever estimate people's probability when housing price inevitably goes down? No, you can't. Right. So in other words, the correlation doesn't tell you because you are estimating probably from correlation, historical correlation. It doesn't tell you what will happen if, for example, housing prices start to go down in the future. And unfortunately, people don't really see that as a problem because they don't understand the mechanism. Right? They don't understand why people have low default probability during the last 20 years. Because they don't understand the mechanism, they just wrongly believing the historical correlation induce the probability, and they use it to price their assets, and those assets are hugely overpriced as a result. Right? So this is sort of like a more realistic example of not understanding mechanism and relying too much on correlation or historical data will give you. Okay, this is another fun example about causality and about statistical relationship. It's called the Simpsons paradox, and I'm not sure how many of you have heard about the Simpsons paradox, but it's a very famous paradox in statistics. So here's the idea, right? So there's a drug I can give you. The drug will let's first take a look at combined data. Okay, so I have 35 people who have received this drug, and 78% of them recovered. Okay, so there's people who, out of 350 people, 78 of them recovered, and you see out of 350 people, 83 of them who have not received the drug also recovered. So people who receive the drug, people who take the drug, recover at a lower rate than people who do not take the drug. So question, is this drug good or not? Good or bad? So, people who take the drug recover at 78%. People who do not take the drug recover at 83%. It seems that taking the drug makes you worse off. Until, of course, we look a little bit more closely. So let's divide the population into men and women. Now, if we look at the men, it turns out that out of these 350 people, most of them are women. A smaller percentage of them are men, minority. Out of the men, 93% recover if they take the drug. 87% if they don't take the drug. Out of the women, 73% recover if they take the drug. 69% recover if they don't take the drug. So in other words, for both men and women, this drug, taking the drug, improved their recovery rate. Right? Okay? Alright, so is this drug good or bad? Is it good or bad? First of all, why do we see this reversal? This is a reversal in correlation, right? So in aggregate, if we do not divide the sample by man and woman, then there is a negative correlation between taking the drug and recovery. Taking the drug negatively is correlated negatively with recovery rate. But once we divide the sample into man and woman, then within each sample, within each subpopulation, it becomes a positive correlation. So the negative correlation becomes a positive correlation once we divide the population into subsamples, subpopulations. Why? Why is that? Can you think about the reason? It's very obvious. I hope it's very obvious. Sorry?
Gender ratio.
Gender ratio. So why would the gender ratio make this reversal?
In a no job case, it seems that the weight on the man is larger.
The weight on a man is larger? What do you mean by the weight on a man is larger? There are more women than men. Right? There are more women than men.
In a no job case.
Oh, the no job case, yes, of course. Right. So you are on the right track. The reason why we have this reversal is called a composition effect. Because the population is composed of more women. Well, out of these three, the population who take the drug is composed of more women than men. The population who do not take drug is more men than women. And a woman has a naturally, for this disease, woman has a naturally lower recovery rate. So for people who take the drug, if more of them women, then they bring down the overall recovery rate, right? Because they are naturally, they have a lower recovery rate by themselves. So even though it's good for men and good for, I shouldn't say good, even though it's positive for men, positively correlated for men, and positively correlated for women, because woman has a lower level, and because they make up the larger percentage of the people who take the drug, in the end, people who take the drug will have a lower percentage of recovery. Right? So this is pure composition effect. Okay, pure composition effect. Now, this Simpsons paradox it happens in reality a lot, meaning oftentimes when we go from subpopulation to bigger population, the correlation changes signs. Okay, a very prominent example of aggregation reversal documented by many political scientists in the United States is who supports Republicans and who supports Democrats. Now, if we look at a single individual, then it turns out at the individual level, the richer you are, okay, the more money you make, the more. Any people know about U.S. politics? If you become richer, are you more likely to be a Republican or a Democrat? Do you know? Yes. Okay. Good. So richer is associated, positive correlated with being a Republican, okay? All right. However, if we aggregate people into states, okay, different states of the U.S. Okay, so this is California, this is New York, for example. So if we aggregate them into states, the richer the state, the more Democratic, okay? Democratic. And the reasons why. Why is that the case? Well, it's a simple case of aggregation reversal, which is very similar to the Simpsons paradox here. Okay? Well, it's because, right, the rich states and the poor. So people can figure out why. Do people know? Simply by looking at it, what's happened between the rich state and poor state? I won't name any poor state, but actually, let me name it, right? Kansas, Alabama, right? So these are poor, right? Okay, I'm sorry for those states, but what happens between, so in each state, okay, within each state, it's true that the richer you are, the more likely you are going to be a Republican. Okay, it's always true like that. But once we aggregate it, so here, people are much richer than this place, they are more. Here, the people are more democratic. All right, so can you figure out why? It's very similar to The Simpsons. Right? For the Simpsons, if you take a look at, if you aggregate man and woman, so within man and within woman, it's all positive correlation. Okay, but once you aggregate them, it becomes the other direction, and right, becomes the other direction once you aggregate all of them. It's because some of them have a natural, not natural, but some of them have a higher. Some of them is composition, right? So man and woman composition. Well, a lot of people have written papers about this topic, right? But there are many explanations for aggregation reversal in political attitudes. But let's just imagine some very extremely simple case. Okay, extremely simple explanation. People care not only about money, right? In politics, people care not only about. So the reason why richer people support Republicans is because Republicans tend to be the lower tax party, so they want to lower tax. Democrats want to have higher tax and help the poor people, so that's why they tend to favor higher tax, and rich people want to support Republicans. Okay. But it turns out also that people care not only about taxation, right? People care not only about the money in their pocket, which makes some people Republican people. People also care about other things, like social values, for example. Okay, so for example, some people may support, gay marriage, and people may support anti-abortion, and some people support abortion. They are more religiously conservative, and they are against gay marriage, etc. Right? So people differ both on the economic dimension and on social dimension. Right? Okay. All right. So one possibility is in these four states, right? People are mostly socially conservative, and here people are mostly socially progressive. Progressive means they are on the same base. But anyway, okay, so they differ along the social dimensions, and for people of the same social values, the higher the income, the more they are likely to be Republican. Okay, so it's true in each one. But people who are progressive, people of certain social values, like progressive people, tend to, on average, have a higher income than people who are lower social, people who are more conservative social values. If that's the case, then we will see this aggregation reversal. Okay, so that's one explanation. Just like what? Just like people here differ by their man and woman, by their gender. Right? People in that case can be differed by their social values. So even though there's a correlation between drug and recovery, because people also differ not only by their recovery, they also differ by their man and woman as a gender. In this case, the social value that will create this kind of aggregation adjustment. Okay. You can think about it, right? Okay. So question here. Is this drug actually good or not? Still this question. Is this drug good or not? Is it a good drug? Is it a bad drug? So it's good for men, it's good for women. If you aggregate them, it's reversed. So is it a good drug? Effective? If you're a doctor, if you look at the data, are you willing to prescribe this drug?
Yes.
Because? Because it's good for men and good for women. Okay. What if I divide men into, again, two groups? Tall men and short men. Is it possible that for tall men, the recovery rate is lower? For short men, the recovery rate is lower, but on aggregate, it's higher. Is it possible, right? So here's the idea that this is the whole population. On this whole population is negative. The correlation is negative. Taking the drug, lower recovery rate. Once I divide it into man and woman, it becomes positive, right? Taking the drug is positive recovery. But what if I divide them further into tall man and short man and tall woman and short woman? Is it possible that the correlation will again become negative, negative, negative? Of course, yes, right? And so does that make the drug bad again? And what if I further divide them into tall and handsome, etc.? So you can do all these things, right? You can do all these subdivisions, and you never know. So what's the point here? The point here is, number one, simply looking at statistical correlation by itself is very hard. It's not going to tell us the causal effect, right? Because all we are doing here is statistical correlation. We're looking at correlation in different subsamples. And simply looking at it without adding any other assumptions, we're not going to discover the true causal relationship. Because in the end, what we are interested in is in the causal effect. So when I say, is the drug good or bad? I'm asking what? I'm asking a causal question. Okay, I'm asking, if I give you the drug, is it going to increase or decrease your probability of being cured? That is a causal effect of drug. But we are trying to look at statistical relation without adding any assumptions. In that case, we cannot do that. Okay, it will not tell you the causal effect. As we will learn, anytime we do causal inference, we actually cannot rely on data alone. We cannot rely on statistical pattern alone. We have to also rely on some causal assumptions, which is important to truly derive the causal effect of interest. As we will learn that. Okay, don't worry about that. But so one lesson here is simply looking at the statistical relationship is without adding any causal assumptions not going to tell us the causal effect. Okay, so that's the first thing. The second thing is, imagine, well, underlying this data, right? Underlying our observation here, there has to be a true causal effect. The true causal effect is this drug is effective or not effective. That's it. Okay, right? And the true causal effect will not change depending on whether you put the subpopulation, whether the people are tall. Well, unless this causal effect itself changes with, maybe this drug is truly good for men and bad for women, or good for tall versus short. But typically, for the drug, it has a pretty stable causal effect. But what we see here is that if the statistical correlation is highly unstable, okay? In other words, if I look at man and woman, it's one sign. If we look at tall versus short, it's another sign. If we look at intelligence, it's another sign. So statistical relationship is unstable. So that's another point that this example shows. Right? Causal relationship tend to be more stable. Causal relationship is how the world actually functions, right? It's the underlying relation. Statistical correlation completely depends on what population you look at. Some population become positive, and you can, right? So you look at the whole population, it's negative. You condition on gender, it's positive. But if you condition on other things, you further condition on height and appearance, etc., you can always flip the statistical correlation. So statistical correlation is unstable. Right? So that's another point of why we should do causal inference. Because simply look at statistical relationship is notoriously unstable and depends on what the population you're looking at. Okay. All right. So that's hopefully the another motivation for why we should do causal inference. And finally, why we should do causal inference is because AI. Right? Now we know that AI is developing very fast today, but what is the ultimate goal of AI? Because currently, what people are called, what people in computer science today call AI, it's not really true artificial intelligence, because those things have no intelligence. Right? So we can build a deep neural network to recognize images. So what? Okay, great. All right, you can recognize images, and you can recognize voice, and you can recognize letters, etc. But that's not true. That's not true intelligence. In order for a robot, in order for an algorithm to have true intelligence, the algorithm has to be able to think. And what do we mean by thinking? We mean it has to be able to do causal inference. It's really that simple. Okay? The true hallmark of intelligence is being able to look at statistical patterns and draw causal inference from it. Okay? Understanding what is the underlying mechanism that generates the data. That's the true hallmark of intelligence. Before you're able to do that, okay, if you cannot do that, then all you can do is simply look at a pattern and then try to discover pattern. Okay, discover pattern from a statistical data. That's not intelligence. You still cannot think. Okay, so causal inference is the future direction of computer science and of artificial intelligence. And today there are already a lot of people in computer science are starting to do causal inference. Okay, now traditionally causal inference is like what we social scientists do, right? But in the future, this is going to be a future direction for computer science too, because that's really true where the true artificial intelligence actually come from. Right? You have to be able to think about what generates the patterns. For robots, right? You receive information from the environment continuously, So the goal for doing causal inference for robots is how do a robot that that continuously receive information from the environment to continuously be able to improve its causal inference model. Right? So this is the research that people have already begun doing. Okay, all right. So back to so this is the future stuff. But back to what we're doing in basic causal effect learning. I already introduced this do operator in my introduction. Do means do A equal to A means we set set X equal to A, right? So there's the difference between causal inference and statistical relationship is doing versus seeing. Statistical relationship is seeing, right? So you see a correlation, and without being able to intervene it. Doing is you can actually actively intervene on the pattern, right? You can change the value of X, and then you see what the value of Y is. Okay, so that tells you the causal effect. X and Y can be correlated, but if you change X, nothing happens to Y, then there's no causal relationship. Okay, so it's very simple. Seeing versus doing. All right, doing it. In fact, some people will go so far as to say that the ability to do something, to change the value of X by yourself, is the very foundation of causal inference. Meaning, if the value of the X cannot be changed, even in theory, then there's no point of ever talking about causal inference. So every time you want to say, I want to know the effect of X on Y, you have to think about how you are ever able to change the value of X. If you can never change the value of X, then what does it mean to estimate the causal effect of X and Y? Okay? So this is the point of Holland, who said, the whole point of X having causal effect on Y is that we can change the value of X, and then it has an effect on Y. But if it's impossible, even in theory, to change the value of X, then what does the causal effect mean? So many people use this point to point out that a lot of questions that we ask in our studies, right, in our research, many of the research questions we ask do not actually make a lot of sense. Okay, so for example, people may say, what is the causal effect of your height, okay, on the amount of money you earn? Right? So in labor market studies, people talk about appearance, beauty premium, and height premium, right? So the idea is the people who are prettier and who are taller earn higher salaries. It's true, absolutely. Okay, so if you look at any labor market, China, US, whatever, you see that people who are taller and rated higher in terms of appearance tend to, everything else being equal, tend to earn more money. So then people have written papers about the causal effect of appearance and height on the money you earn. Now the question is, what does causal effect actually mean, right? So suppose I say the causal effect of height on earning. Can you actually manipulate height? Can you actually change people's height? You cannot. So what does that actually mean, right? So this causal effect like that, many people believe that causal effect like that is not well defined. In the sense that in order for a causal effect to be well defined, you have to be able to change X, even in theory. Okay, you can say, what is the causal effect of democracy on economic growth, for example. Well, at least in theory, you can think about, even if you're not able to do it, but at least in theory, you can think about, going to North Korea and then change it or something. Right? So let's not talk about China. Anyway, so that's possible to think about an intervention. But that brings to another question, which is you see people doing research on democracy effect on growth. Right? When I'm talking about that, I'm talking about actual research field. A lot of papers are written on this topic. But the typical way people do it is to do some regression with economies that are democratic or non-democratic on the right-hand side and GDP growth on the left-hand side. Right? So they regress GDP growth on, for example, whether this country is democracy or something, and then they control a bunch of variables. But if you do that, what is the so when we say we do X equal to A, this kind of do thing is often called intervention or manipulation, okay, or treatment, right? The speculation is called treatment. So when you regress GDP growth on democracy, what is the treatment or what is the manipulation you're actually thinking about? Are you thinking about going into a country and just kill all the leaders, right? And then you install a democratic government. Or you think about, so what is the treatment? Or are you thinking about going to a country and asking people to peacefully request a transition? Or are you going to think about some other ways, like the United States going to Iraq and something like that, right? So what kind of mechanism are you thinking about? Because this different kind of treatment will give you very different, will potentially have extremely different causal effect. Right? So in other words, if you read a lot, so it's very helpful, whenever you do causal inference, it's very helpful to imagine, or at least to think about, seriously, what is the treatment you are actually thinking about before doing the research? Because if you read these papers, it's not clear. It's not clear at all what the treatment they are thinking about. And there's lumping every democratic country together. Some have been Democrat forever, some guys very shortly. And so in the end, the causal effect they estimate has no clear meaning. Right? So in other words, right, so this is the one point I truly want to make, which is in order for your causal effect you want to estimate have true meaning, you've got to think very carefully about what exactly the treatment is, right? What is the manipulation you are truly doing? Okay? All right. Anyway, so we say that if I want to estimate the causal effect of x on y, then what I'm doing is I want to know Ey given do x equal to a. Okay? So if I personally change the value of x to a, if I change the value of x to a, what is the effect on y? Okay? If we do statistical prediction, then we know Ey given x. Right? So this is statistical prediction, and this is causal prediction. Causal prediction means if I change x to a, what the effect on y is. Right. Okay. It's a very simple way of writing the two things. Okay. Now, so this is some basic introduction to the concepts. Now we're going to seriously discuss some causal inference framework, right? So models that help us to conceptualize causal inference. The first framework we're going to talk about is the Rubin causal model, or the potential outcome framework. This has been the dominant causal inference framework for a long time. It originated, well, not that long, but a couple of decades. And it originated in statistics. So it's developed by Rubin of Harvard in the 1970s, where he came up with this potential outcome framework. Okay. Today, so in this lecture, I'm going to introduce two models for modeling causal inference. The first one is the Rubin causal model. And the second one will be, which I will discuss later, will be the causal diagram, or the causal, or the graphical causal model. Okay, so causal graphic model. So that's the second one. We'll begin with the Rubin causal model. So the Rubin causal model is a model for causal inference that conceptualizes observed data as if they are experiments. Because the Rubin causal model comes from thinking about experiments. So even though in observational data we see all kinds of data, but we're going to try to think about them as if they're outcomes of experiments. Okay? Now, some of them may be actual experiments, but most of them you can think about as experiments conducted by the subjects themselves. Okay, so we'll see what that means. But the model utilizes the analogy of experiments so that whenever we want to know the causal effect of x on y, using the language of the Rubin causal model, we say the x is a treatment and the y is the outcome. So why do we call x treatment? Because in experiments, that's what people call, right? So when you do experiments, you treat some subjects and you put other subjects as control, okay? And you compare the treatment versus the control. So we're going to use this language. And it's important that you know that this is only a language that we use. It's not actual treatment or whatever, okay? So we're going to say whenever we want to investigate the effect of x on y, we are going to say x is a treatment or intervention, and y is the outcome. For example, suppose I want to know the causal effect of college education on your earnings. Again, an example everybody familiar with, right? The college education is called a treatment. You can sometimes talk about the causal effect as a treatment effect. So you say the treatment effect of college, right, on earnings. Okay. All right. So so the second thing is, let's suppose x has different values. Now, I will talk about the shortcomings of the Rubin causal model because I don't like the model very much. But I'll talk about shortcomings later. But here's one shortcoming, which is because it uses experimental language, it's hard for this model to actually conceptualize or think about continuous treatment. Okay, x Because x can be anything, right? We want to know the causal effect of x on y, and x can be anything. Okay, it can be continuous and categorical. But because Rubin causal model come from the experimental tradition, the most natural way to think about x is at the 0-1 binary variable. Because experiments, that's what people do, right? I give you some people treatment, some people no treatment, 0-1. Okay, so now let's just imagine the 0-1 x, okay? In the 0-1 x, the Rubin causal model says what you see is the y. But what you see is now what's underlying. Because underlying, there are actually two random variables called y0 and y1, okay? And y0 means the outcome if the person received treatment 0, x 0. Okay, and y1 means the outcome if the person received y1. And so depends on for this person, for each individual, we can define yi1 and y0. Okay, and if this person xi means the treatment this I gets, if xi equal to 0, then the outcome yi will be equal to yi0. If xi equal to 1, then the outcome is y1. That's it. Okay. So in other words, the Rubin causal this is called potential outcomes. These things are called potential outcomes. They're not real. They're potential. So when potentially for every person, let's imagine there exists yi0 and y1, and then depends on what this person actually receives. The outcome is one of them. Okay. So that's the idea behind this framework. All right. Now, suppose this person actually receives xi equal to 1, then yi equal to yi1. In this case, we call yi0 counterfactual. Counterfactual. Okay. So this case, this is called a counterfactual outcome, and this is called a realized outcome because they actually received treatment equal to 1. And both of them are called a potential outcome, right? So before receiving the treatment, before receiving x, the person has these two potential outcomes. After receiving xi equal to 1, he has the realized outcome and has the counterfactual outcome. So counterfactual outcome means the outcome that has not been realized, right? So it is defined in the Rubin causal model. It's defined as the distribution of yi1 and the distribution of yi0. So in other words, these are potential outcomes. Okay? And so causal effect is defined in terms of potential outcomes. So if this is not equal to this, if they are not equal, then we say x has a causal effect on y. Because if x has no causal effect on y, then they should be completely equal, right? So in other words, the distribution of y should, by receiving the treatment of x equal to 0 versus the treatment of x equal to 1, should have no impact on y. In that case, they should be equal. But as long as x has an impact on y, then receiving x equal to 1 versus receiving x equal to 0 will give you different distribution of y in the end. Okay, so that's related to the potential outcomes. So if they are not equal, we say there is a causal effect. And how do we define a causal effect? Right? Because as long as they are not equal, it's a causal effect. But how do we actually measure the causal effect? Right? Well, you can think about causal effect as a distribution, simply minus. But typically, when we say we're interested in the mean. Okay. So we define the first thing is called the average causal effect, ATE. Basically, the mean causal effect is basically this, okay? So the ATE, the average causal effect, is simply defined as the expectation of the y1 minus y0. So let tau, let me define tau equal to y1 minus y0. This tau has a distribution, right? Because it's a random variable. It's two potential outcome random variable. Now, if we calculate the expectation of this random variable, then that's the average causal effect or average treatment effect, the AT. Now, we can also speak about the ATT, which is the average treatment effect on the treated. What does that mean? That means expectation of y1 minus y0 conditional on x equal to 1. Because why? Because by doing conditional like this, we mean the people who actually receive x equal to 1. For them, what is the causal effect? So the average treatment untreated is a causal effect for people who have received the treatment. All right? And of course, there's also the ATU, the average treatment effect on the untreated, same thing, okay, which is E tau given x equal to 0. Okay? That's it. So typically, people often compute these three summary statistics. Because tau, y1 minus y0, is the treatment effect. Okay? That's the causal effect. But this causal effect is a distribution, right? Because it's a random variable. Now, you can think about AT, ATT, ATU as simply three kind of summary statistics about this distribution. Okay? The mean or the mean condition x equal to the mean condition. Right. By the way, why are they different? Why are they different? Why are they not the same thing? So in what situation is the average treatment AT different from ATT? You don't have to look at ATU. That's okay about it. Right? Between ATT and AT, in what situation are they different? Sorry?
No causal effect.
Well, if there's no causal effect, why would they be different? Wouldn't it be just 0 and a 0 here? Sorry? Not a lot of people get the treatment. That just means this set is small. Okay, some people who you think you're giving the treatment, but they end up do not get the treatment. So what? The answer is people who get the treatment are different from people who do not get the treatment. So in other words, the causal effect is different from people who get the treatment versus people who do not get the treatment. Right? This tau is different for people who get the treatment versus people who do not get the treatment. In that case, these two are different. Right? Okay. So in economics, selection effect is what we're talking about here. All right? So people who go to college versus people who do not go to college, they're different. So in that case, the causal effect for the entire population will be different from the causal effect for the people who actually go to college. Right? So that's you know. So, okay. So here's an illustration, okay? Suppose this is the distribution of y0, the potential outcome of receiving no treatment. This is the part distribution of y1, the potential outcome of receiving the treatment. Then the AT is the difference between the mean, okay? Because the AT is the mean of the difference. But the mean of difference is the difference of the mean, okay? Right. All right. So one way to think about the potential outcome framework, we are running out of time? Yes. Just a few more words, okay? So one way to think about the potential outcome framework is that instead of our observed data is a distribution of x to y, right? X, y are our observed variables. But underlying this x, y is actually the joint distribution of three variables, which is x, y1, and y0. So x is a binary variable, okay? So then, indeed, the underlying distribution is this three-variable distribution, joint distribution. But we only observe x, y, because y is either 1 or this one, okay? Right, so that's one way to think about it. So this becomes our underlying distribution, right? X, y1, and y0. Now, we can always talk about causal effect at a population level, meaning as long as y1 and y0 are random variables, they have a distribution underneath, then we can always talk about causal effect. But if we are talking about causal effect at the individual level, then we are running into trouble, right? So suppose I only look at tau I is yi1 minus y0, which is the individual causal effect. But what is the treatment on this particular individual? Not on the population, but on this particular individual. Then we run into trouble because we can never know this. Because for each individual, we only observe one of the y's. for the population, we observe y1 for some people, we observe y0 for other people, and there's a way to tell them apart. But to calculate the causal effect. For each individual, it's never possible because we only see one of them, and that's it. That's it. So tau I for individual treatment effect can never be known. Okay. So that's the fundamental problem of causal inference as well. So here's the example, right? If the influenza vaccine prevents me from getting the flu, now if you get the flu, you get the vaccine and you didn't get the flu. So this is what actually happened. I got the vaccine, I did not get sick. So my actual treatment is equal to 1. My observed outcome is y1, which is my potential outcome under treatment. Now, what would happen if I have not get the vaccine? Would I have gotten sick? That's the question, right? If I didn't get it, would I be sick? That's the counterfactual question. So, which is my counterfactual treatment is x to equal 0, and my counterfactual outcome is what is y0. But you never know that. You will never know that. You're just one individual, so you will never know that, right? Okay. So this has been called sometimes it's called a fundamental problem causal inference, in the sense that you never see the counterfactual for each individual. Okay? In fact, Rubin himself said that. Right? Rubin is the one who invented the Rubin causal model. So Rubin actually has this insight, which he said that causal inference is fundamentally a missing data problem. He said, because we only see one data, we don't see the other data, so it's a missing data problem. I don't really like this because why? Because actually I think he's overcomplicating stuff. Because why? Because every problem is a missing data problem. What do I mean by that? The statement that causal inference is a fundamentally missing data problem make this seem as if this is a causal inference problem, not a statistical inference problem, not a statistical problem. But it turns out whether you are doing causal inference or you are doing prediction, you can always think about things as missing data problem. Right? What do I mean by that? When we do regression, what are we doing? So this is a data point. This is a data point. Okay? And then you do a regression. And then you predict the y hat to be here, right? Okay, what does this prediction mean? It means that you are thinking about your regression model. Your regression model is y equal to, there's this line, right, fx plus e. So you are thinking about, at each point, your model is there's many underlying y, right? Okay, there's many underlying y, but you just don't see them. You only see one realization. Or maybe you see some other realization here, but you do not see all the realization. And that's what you're doing with your prediction, is you're trying to predict the mean of all the underlying population, right? So is this also a missing data problem? You can also say that. Because you only see one realization, you don't see the other realization. If you see all the realization, you see the population. Then there's no point of doing any statistical analysis. Okay? So it's the same thing as causal inference. Causal inference says you only see one realization without seeing the other. That's why you have a problem. Well, for this one, I also see only one realization. I never know what happens if I get a different E, what happens. Just like I never know here, if I get a different X value, what happens, right? So it's the same problem. Okay? That's why I think this insight is overrated. But anyway. Finally, okay, we only have, let me just, one more. So this is just an illustration where we have treatment x equal to 0, x equal to 1, observed outcome, potential outcome. So if I have these two potential outcomes, then if x equal to 0, I only see this. X equal to 1, I only see this. Now, if I naively put the y, plot the x versus the y, then I see this, okay? So when x equal to 1, I have very high y value. X to 0, I have very low y value. But you cannot really just compare them directly, because underlying them is actually two sets of potential outcomes. And what you really do is compare this potential outcome versus this potential outcome, not compare these value versus these value. So this is an illustration of why it's improper to conclude causal effects from statistical correlation directly without thinking of it. Okay. All right. So I'm done. Okay, I'm done today, and we can continue next week.